Recording in progress.
So thanks, Kathy, for the introduction. The first thing I would like to do is motivate the title of the thesis. It's called Information Processing with Photonic Hardware Neural Networks. And I want to motivate the use of photonic structures for information processing. You may have noticed that in the last years, artificial intelligence applications are around. You can see them in autonomous cars that get to know all of their surroundings. You can see them in games. There are machines that can play against the most brilliant brains in games such as chess or Go. You can see them in robotic arms that are able to perform complex interventions, or even in speaking assistants. At the heart of all these applications, we have neural networks that are seeking to extract useful information. However, in order to make them more accurate and robust, we have seen a tremendous increase in the training compute over the last years, especially since 2010, when we introduced deep neural networks. With training compute, I mean everything that is needed to train a neural network, such as memory, time spent, or energy consumption. And regarding energy consumption, one can see here in these graphs the common footprints of some benchmarks, such as human life, a car during its whole lifetime, or the transformer. The transformer is a previous version of what we know now as GPT-3. It used to have 600,000 parameters. If you make the maths, nowadays GPT-3 uses 1.75 billion parameters. So just an incredible carbon footprint. And on the top of that, we have these neural networks that are implemented in von Neumann architectures, the ones of our computers. And they have separate cells for memory and processing. So there is a continuous flux of information between the two that is introducing a time latency. Because of that, we have seen several alternative approaches that are implementing hardware neural networks that are looking for in-memory computing. So there is not this flux between information and processing cell, between memory and processing cell. They are looking for lower energy consumption. They have to be scalable, and it would be nice if they use parallelism. And of course, they have to find a trade-off between cost and effectiveness. Some examples of those kind of alternative approaches are FPGAs. These are reconfigurable devices that allow for in-memory computation. We have application-specific integrated circuits. For example, one can think about TPUs. Those were specific devices that were built by Google in order to accelerate machine learning with matrix vector multiplications. Now they can be even a full category on themselves. We have memristor-based architectures. These are two-terminal electric devices that can allow for memory and also computing. And then we have neuromorphic and neuroinspired architectures. We know that our brain is such a powerful tool that can compute, and we consume not that much. With neuromorphic, I mean this kind of structures that mimic certain functions of the brain, for example, the spike between neurons. And those can be spiky neural networks, or neuroinspired, that just these kind of architectures that look for all of this. And within that, we can have photonic computing. Why to use light for computing? Well, we can reach multi-gigahertz bandwidths. It can exploit parallelism, either by splitting the light and even working in different kind of wavelengths. It has low power energy consumption compared to electronic counterparts, and it also allows for in-memory computing. One can think about these phase change materials that allow for memory. Because of that, in the last years, we have seen several implementations. For example, here we have this one that is based on wavelength multiplexing. This one that is a mix of Mach-Zehnder interferometers. We have free space optics or in-fiber optics. So that's the main motivation for using photonic structures. Now I would go through the index of the talk. First of all, I will give you some introductory concepts to explain the neural network that I'm going to implement in hardware, that is reservoir computing, and in particular, time-delay reservoir computing. Then we will see how to accelerate the operational speed of this device by bandwidth enhancement. And this is reflected in these two papers that were in Nanophotonics and Optics letters. Later, we would see how to compare this kind of photonic processing scheme against digital ones. This is another paper that was published in GLT. And finally, I will talk about other kinds of architectures that can be implemented in photonics, and we will wrap up with some final remarks and perspectives. So let's go with the introductory concepts. We know that there is a vast amount of neural networks, and when I say it, I mean it. Every kind of these neural networks uses different kinds of cells. This is the time invariant regular cell. We have memory cells with different kinds of gates, and we have also these spiking cells that produce binary outputs, for example. Each of them is meant for a particular task, but the most used ones are feed-forward neural networks and recurrent neural networks. In feed-forward neural networks, the information flows in one direction, and then you need to train back all the weights through backpropagation. They are good for tasks that are time independent, such as pattern recognition. If you want to solve tasks that have time dependencies, you may be interested in using this kind of networks that are called recurrent neural networks that have recurrences, so they introduce memory, and they are good for time series prediction. Within this particular set of recurrent neural networks, we find reservoir computing. Reservoir computing has the characteristic that the connections from the input to the reservoir are fixed, as well as all the connections within the reservoir. And the only thing that you have to train are the connections from the reservoir to the output layer. And this is done by just using linear regression. Here I just plotted one input for visualization. There can be several, same as the output. They have to fulfill some requirements. There has to be some fading memory, so the information has to stay within a while in this reservoir. There has to be dimensionality expansion and nonlinearity, meaning that if we have an input, it has to be spread all over the network, and we have to recover different nonlinear responses. Good news is that there are many possible reservoirs that can be used. We have electrical circuits, spintronic devices, chemical reaction networks, microfluid systems, mechanical resonators, and of course, photonic structures. We're going to use a particular way of looking at reservoir computing that is called time delay reservoir computing. In this kind of approach, we replace the fully connected neural network by just one single nonlinear node subjected to feedback. And still, it fulfills the requirements. We have the fading memory that is introduced by this recurrence in the net. We have the nonlinear transformation by the nonlinear node, and we have the dimensionality expansion. And this is the key of this approach. Imagine that you want to process this input, this U, then you will have to sample this value and hold it for a period of time that is equal to the delay length. And over that, in order to obtain the different responses that are going to define the virtual nodes in the net, you have to put a mask. This mask is a set of random values that is going to be fixed for the whole duration of the task and represents the input to reservoir connections. So input, mask, masked input. This masked input is entered into the reservoir, flows, and here the information is mixed with the next step. The only thing that you have to do now is to train the output layer as usual to define the output connections, the output weights. For the reservoir, we can use just a laser that is subjected to delay feedback, and in order to introduce the information, we can use another laser that is modulated. One has to fulfill certain conditions regarding time scales. As any physical system, it will have a response time. If you choose the injection rate, so how fast we input the information, that in this case is defined by the virtual node separation, too short with respect to the response time, then we will observe a flat response. If this time is too long in comparison with the response time, then the system will have time to respond and reach a steady state. If that is the case, then the only connection within the virtual nodes in the reservoir would be given after a round trip. So we will have this kind of connections. We're not interested in that, so we're going to use an intermediate regime in which both scales are in the same order of magnitude. Keep this in mind, because together with that, we have a system created by a drive and a response laser. And there are certain dynamics that we have to look at. So the drive laser is emitting at a certain frequency, same as the slab, and the difference in both is called the frequency detuning. For certain conditions, imagine we are in this injection rate, the lasers are going to be under the injection locking condition, which is that the slave laser is following the emission of the drive. This is achieved in this kind of frequency detunings. Out of that, the lasers would be unlocked, so operating at their own. If we introduce feedback into the system, that adds another player, so there is a competition between injection and feedback. Notice that here we have the same graph that now is tilted 90 degrees. Here we have the frequency detuning and the injection strength. The black would be no feedback, so we recover the cone of injection locking, while if we increase the level of feedback in the system, then we would need a higher injection in order to reach the injection locking condition. And on the top of that, now we have our time delay reservoir. We have a drive laser, but it is modulated. So we have a modulated injection entering into the system. And in that case, we have, as I said, the injection locking, meaning that the slave laser is working at the frequencies of the drive. We see this on the optical spectra. If the lasers are unlocked, we have independent emission of the lasers, here the drive, and here the response laser that is broadened because of the feedback. And then we have an intermediate state in which full locking is lost for some time intervals. And this is represented by the drive laser that we see here, and the response laser that is being affected by this response. So we have to respect some time scales. We have different operational regimes. How is this implemented in hardware? Well, going from the schematics to the lab, here we see the injection laser is isolated. Here we apply the modulation through a Mach Zehnder modulator. Here the signal that we feed is in the arbitrary waveform generator, enters into the reservoir with this attenuator here that is controlling the injection strength. So masked input enters, suffers the nonlinear response with the interaction, and here at the coupler, it can either go back and the feedback strength is controlled by the second attenuator, or it's isolated and used for detection. And then with the output layer offline. How is this in the lab? Here we have the two lasers, injection and response. The output of the injection laser goes through the Mach Zehnder modulator. Here we have the input from the AWG. And well, here we have a controller, but the input goes here. Here we have the masked input, enters into this first coupler, and then suffers the nonlinear response, and it can go out. Here we have the second coupler that is here. Part of the signal goes back and closes the loop. Part of the signal goes out for detection. So this finishes the first part. I want you to remember some key concepts. Reservoir computing is a hardware-friendly implementation of neural networks. Second, in time delay reservoir, the recurrent connections are provided by the delay loop, and you have to choose a property, the separation of the virtual nodes with respect to the response time. And finally, there are different nonlinear transformations that occur depending on the feedback, the strength, the injection strength, and the frequency, the tuning between both. We know that this kind of approach works. It has been demonstrated and characterized. So we were wondering, how can we go faster? If we are processing every piece of information, its delay time, then first thing would be to reduce the delay lane. But in that case, you would have to reduce the number of virtual nodes. And you may not be interested in that. So you will need to reduce the separation between the nodes, so the virtual node separation. And in such a case, in order to be working in the timescales that we want, we have to reduce the response time. And this is what is this second section going to be about, how to accelerate photonic computing. So we want to increase the modulation bandwidth. Those are analogous things, increasing modulation bandwidth and decreasing the response time of the system. If we want to use standard semiconductor lasers and get profit from this master-slave configuration, we know that a strong injection lock in semiconductor lasers exhibit enhanced bandwidth response with respect to the free-running case. This was demonstrated long ago. Here we have in the frequency detuning parameters in the injection parameter that the region of a stable locking is increased. That's what we saw before. And additionally, we have here that the injection parameter is modifying the resonance frequency of the system. So from the free running case that we had 3 GHz, we have now increased it up to 10. If resonance frequency increases, that is directly related to the bandwidth, so we increase bandwidth. And we wanted to prove that for our time delay reservoir computer, and we started to model it numerically. And for that, we used the Lang-Kobayashi rate equations with addition of an optical injection term. And here we have the system with the feedback plus the injection term. The 3 important parameters that we have here are feedback strength, injection strength, and frequency detuning between lasers. For the time delay reservoir computer, we defined 80 virtual nodes separated by 12 or 100 picoseconds, and correspondingly the delay lengths of 960 picoseconds and 8 nanoseconds. The response bandwidth of the system was defined as the frequency interval between the component, excluding it, and the frequency that contains the 80% of the total power spectral density. We did that for 2 levels of optical injection when the parameter was equal to 0.4, that in our system was around 0.1 milliwatts, and for the parameter equal to 2, that is 0.5, 0.6 milliwatts. The first thing that we can observe is that indeed the bandwidth response is increased, going from these blues to these greens, and we have a deeper loop in what is happening. For example, for zero frequency detuning and some level of feedback, we have this. In red, we have the moderate injection. We see that the response is here, around 60 GHz. And for a high injection, we have this spectra here, and the bandwidth is around 20. One needs to be aware that in this kind of graph, the value that we are recording, the bandwidth response, is valid when the lasers are locked or close to lock configuration. If not, we will be just measuring the frequency detuning between lasers. So we have here at 33 GHz, we can clearly distinguish for the moderate injection that the emissions are unlocked. Okay, we can see that there is a bandwidth enhanced. Can we use it to increase the performance of our time delay reservoir? And we did that for a data recovery task. I'm not going to enter into the details of this kind of task now. I want to focus on the performance. It's a 180 kilometer long coherent transmission at 1550 and 28 gigabytes per second, quadrature phase shift keying. We train on 2000 binary patterns. We test again 4000. And the error is given by the logarithmic peak error rate, which is the logarithm of the number of bits wrongly detected against the total amount of them. So here we have the error, the lower the better. And in fact, these blues and purples are below the hard decision feed-forward error correction, so the system is correctly operating. For a virtual node separation of 100 picoseconds, we can see that the performance is good for this range of frequency detunings that corresponds to the region in which the lasers are locked or partially locked, and where the feedback is not too high, so we don't get instabilities. If we decrease the virtual node separation and we go 1 order of magnitude less, more or less, to this theta, we can see that there is no condition in which the lasers, in which the system is operating correctly. If we increase the injection strength, we see the following. First, the region of better performance is expanded to wider regions of frequency detuning. And second is that we habilitate a good performance for the time delay reservoir, even with short thetas. So 2 things: increase the region of performance and enable the time delay reservoir computer to work with shorter thetas. We did that also for the Santa Fe time series prediction. This is a well-known benchmark task in which you have to predict the next step of the time series based on the previous ones. And we measured the performance with the normal mean square error. We can see that similar to the other case, we increase the region in which we observe better performance. We don't see that much that the system operates better, because here we're kind of saturating the performance, but still the effect of broadening is observed. Okay, this was regarding numerical results. Then we wanted to see that work in real life, so experiments. And for that, we used the system that I was showing you before, in which we had an AWG that was working as at 10 gigasamples per second. 10 gigasamples per second is a virtual node separation of 100 picoseconds, and the delay loop is defined by the lengths of the different elements, so 16.8 nanoseconds. If you make the maths, then we have 168 virtual nodes available. We wanted to compare with numerics, so in the end, we only use 80 of them. And we compute the performance for the optical data recovery and the Santa Fe time series prediction. Here we see that the minimum error detected is the same, but we have expanded the region in which we observe good performance. So we see that for 2 different levels of feedback and 2 different levels of strength for optical data recovery and also for the Santa Fe time series prediction. Here you see the blue dots are expanded and also shifted to higher values of the frequency decay. At that time, we were only able to achieve this kind of sampling rates at the AWG, but during my PhD, we were able to buy new elements, so we changed the setup and updated it. This one is built with polarization maintaining fibers, so it's more stable, and that's why you see a different value for the feedback loop. And in the AWG, we could reach up to 85.33 gigasamples per second. That defines a delay of almost 10 picoseconds. If you repeat this value 8 times, you could get this kind of virtual node separation, almost an order of magnitude higher, and we would like to compare both. If you make the maths for this virtual node separation and within the delay, you have a space for 260 virtual nodes. So 2 options: either you have a mask with 8 values repeated on a row, which is this kind of virtual node separation, or you repeat the mask 8 times. That's how you input the information. Okay, so we wanted to measure the response bandwidth experimentally, because this is a new setup. And the first thing, and we measured that as the frequency where a 10 dB power spectral density reduction occurs, with respect to the low frequency components we were recording. That was at megagigahertz speed. First thing we notice is that indeed we have an enhanced response of the bandwidth. So from this level of injection of 0.1 milliwatts to this level of injection of 1 milliwatt. Additionally, we recorded where the lasers were not blocked. And that was when we observed a peak of 3 dBs. So if we consider the moderate injection, here, these graphs, we have different spectra. For 0 frequency detuning, we have this blue, lasers are locked. For 10, we have this orange, lasers are locked. And for 20, we can clearly distinguish this peak. So we can observe 2 things. First one, the response bandwidth is enhanced. And second, the region in which the lasers are locked is expanded. To test it, we did the Santa Fe one step ahead prediction, and we tested against the different virtual node separations. Here, we can see that the performance is similar in terms of normal mean square error, but only that when you increase the injection, this area is expanded. If we move to shorter thetas, what we see is that we enable the system to work at shorter thetas and reach the same error, so a good performance. To wrap up everything, we have increased the optical injection to increase the injection data rate of the system. Of course, we are still limited by the loop and we cannot claim that we have increased the processing speed. That is everything that I wanted to mention for this part. So the main results are that increasing the injection strength of the injection laser, we can produce bandwidth enhancement. And this has two effects. First, it broadens the region of optimal performance, and because the lasers are locked for more frequency tuning conditions, and then that it decreases the response time of the system, so we can inject information faster. That means having a shorter theta. The numerical results and the slow operational regimes were published in Nanophotonics, and the fast operational regime was published in the optics letter. Okay. I have explained you the system. I have explained you how to accelerate photonic computing with it. And now we want to see if this kind of a scheme is compatible with digital processing schemes. So for that, we have an optical data communication task. Basically, we encode the information. It can be in intensity, so high levels of intensity, low levels of intensity, and also phase. And what we see is after the transmission line, the signal gets distorted. In particular, there are linear and nonlinear distortions, such as chromatic dispersion, self and cross-phase modulation, or at the receiver stage, we have four-wave mixing. Why to apply this photonic computing to optical data recovery? First of all, we're working in the analog domain, so we may be interested into processing in the analog domain also. And second, if we talk about performance, we have that for low processing speed requirements, independently of the complexity of the task, we have TPUs and CPUs that can perform nicely. If the processing speed requirement is increased and the problem complexity is still not that hard, still there are methods in digital schemes that work perfectly. But we find a gap here when we increase the processing speed requirement and also the complexity of the task in which photonic computing can compete against digital signal processing units. Of course, if the problem is too complex and it has too high processing speed requirements, we cannot solve it. Right. So this is a collaboration with the Optical Communications Group at Kiel University with Professor Panicke, and they gave us the results from their experimental transmission setup. In this kind of setup, they use 5-channel, it's 56 gigabaud, 4-level pulse amplitude encoding, single sideband modulation, and dense wavelength multiplexing. So we're introducing channel interference here. Then the signal is through 100 kilometers, and we directly detect it to obtain 2 samples per symbol. And we can vary the noise, the optical signal to noise ratio, through noise loading. Okay, so we have this kind of signal, as I mentioned, 2 samples per symbol encoded. So these 2 samples correspond to level 00. These 2 samples correspond to level 11. And we want to process that with our experimental setup. So we will have to do this sample and hold operation and masking. 2 things can happen. This is the experimental setup that we have. And we usually know that for this kind of task, we only use 20 virtual nodes. And in our time delay reservoir that we have, that has a delay loop of 24.5 nanoseconds, and we have a virtual node separation of 62 picoseconds, defined by the sampling rate, we have a space for 396 virtual nodes. If we're only using 20 of them, and we use the classical reservoir computing approach, we will process 1 piece of information per round trip. If the mask is only 20 virtual nodes, most of this space is empty. So we're just introducing latency time. One can think about another approach and to introduce more symbols per delay loop, and then the connections, these recurrent connections, would be 1 every 19th symbol. Additionally, we wanted to see what would happen if you open the loop. And if you open the loop, there is no feedback, so you're kind of working with an extreme learning machine. And in such a case, we wanted to compare what was happening if you still have this 1 symbol per delay loop, only that now it's just for comparison reasons. This has no physical sense. And if you introduce all the bits on a row. So that was it. and we started to study what happened if we introduce one symbol per delay. And we saw that if we set 20 virtual nodes, and then we were working for a particular optical signal to noise ratio, the processing time is constant and is defined by the delay loop. And we find that in terms of frequency detuning and optical feedback ratio, the good performance is found between -6 and -16 gigahertz, more or less. So this would be the case of extreme learning machine, open loop, and this would be different levels of feedback. As we see, the lowest error detected is around -3 in all the cases, so there is a limited contribution via optical feedback. If we now introduce more symbols per delay, we have this kind of configuration. If with n equal to 20, 19 symbols can be fitted there, and we decrease the processing time by 19, indeed. And what we observe when we compute the logarithmic error rate was that the errors were down to -3.15, that indeed was lower than the previous case. So we decided to go for the stream learning case, in which you forget about the delay loop and the symbols are introduced one after the other. And here you have a study of what happens when you consider different kind of number of virtual nodes, and this is for 8 different masks. You see that, of course, when you increase the number of virtual nodes considered, the performance goes better, the error is reduced, and when you go for higher number of virtual nodes, the performance decreases and it has a wider variance. However, you may be interested into using this kind of number of virtual nodes, because if this error is enough for your system to operate, then you will operate faster. If you have 8 virtual nodes at 62 picoseconds, that would mean almost 500 picoseconds, so 2 gigahertz operation. In any case, we wanted to compare the performance of the stream learning machine with 20 and 24 virtual nodes, and we did that for different launched optical power. And in this graph, we observe in the x-axis the optical signal to noise ratio, in the y, the error. On blue, we have the linear regression applied directly to the 2 samples that we were receiving. In dark, we have a Kramers-Kronig receiver implementation in DSP. This was done by the Kiel group. And then we have the performance of our stream learning machine, considering 20 in orange and 24 in green virtual nodes. One can observe that from 21 dBs on, the performance of both the Kramers-Kronig and the stream learning machine is below the hard decision feed-forward error correction. The system is operating good. And on top of that, our time delay reservoir is operating even better than the DSP implemented Kramers-Kronig. That's everything from this part. Let's wrap up the main results. We have obtained efficient data recovery for 56 gigabaud PAM4 dense wavelength multiplexing after 100 kilometer transmission. We have seen that there is a limited contribution of the feedback, so a stream learning machine and time delay reservoir computer have similar performance, while stream learning avoids the disadvantages imposed by the delay lane and the feedback instabilities. The better performance are leading to error-free decoding from signal ratios, optical signal ratios above 31 dBs. And we can see that for certain conditions, the photonic signal processing units perform better than the DSP ones. Well, in particular, this Kramers-Kronig receiver. Results are again published in this ELD paper. We're reaching the end. I was going to show you what I did when I was in the research stay in Canada at Sastre Lab in Queen's University. And to let you know that besides time multiplexing, one can use wavelength multiplexing to create the nodes of a neural network. So they have this nice work in collaboration with Princeton, in which they elaborate this broadcast and wave protocol. What I'm going to use is that if you have an input that has different wavelengths, one can use a bank of microring resonator to weight each of them. How does it work? Here we have a microring resonator. We have an input, a through port, and a drop port. The through port is directly to the upper branch of the balanced photodetector, the drop port to the lower branch. Imagine we have a wavelength that is centered around 1533. Then all the signal is going through the through port and will be here. So this would represent a weight of +1. If we have the wavelength centered here, then all of the signal is going through the drop port to this branch, and that would represent a -1. If we operate somewhere in between, then we will be weighting the signal. Of course, we don't want to work with different wavelengths. We're just working with a fixed one, and we want to move the spectra. And to do so, you can apply a current here in order to change the effective index of this microring. So you would be weighting effectively a single wavelength. So my proposal was to implement a tap delay neural networks where the different nodes are implemented by applying different optical delay lines, optical delays to the different wavelengths. And here we have the structure, and each of these branches is going to be represented by a wavelength, and then we will weight them using this bank of microring resonators. How is the experimental setup? We have a bank of semiconductor lasers. Each of them is emitting at a particular wavelength or color. Then we multiplex them and we put all of them together in this input that we modulate via Mach-Zehnder modulator in an AWG. And then this signal is amplified. In fact, I use a saturated amplifier because I wanted to introduce some nonlinearity. And here the signal is multiplexed again to implement the different delay lines. The delays that are implemented here coincide with the sampling speed here. So when they arrive to the multiplexer, we're merging the signal 1 step ago, 2 steps ago, and 3 steps ago. This signal is traveling through the delay line, and through this amplification stage, it enters into an integrated circuit where you introduce the output weights. They are updated just by trial and error algorithms. So if the weights are good, you keep them. If the new ones are better, you keep them. If not, then you recover the previous ones, and that's it. I characterize the maximum output weights. Not all of the lines have the same losses, so that's what you observe here with the different top values. And also have characterized what were the different weights that were applied to each channel. So for example, in channel 3, you can observe all these variations that can be done by varying the injection current to this guy. In order to test it, we tried 2 different tasks. First, the memory task, that is recovering what was injected in previous steps. We can observe that the performance is good and it's kind of the same. And the little disturbances that you find here is because of the different channels that we have for the different steps or nodes. And we also tried that against the analog to digital conversion. So if you have this input string, 1, 1 would represent a 1, 0, 1 is 1/3, 0, 0 is 0, 1, 0 would be 2/3. This is for 2 bits. You can do that for 3 and 4 bits. In our case, we cannot go higher because we don't have memory. But what we observed, it's a good performance, and it was independent on the number of errors of bits that I was considering. This is what I wanted to show. And again, some take-home messages. The main results is that I implement a tap delay neural network based on wavelength multiplexing and different optical delay lines. That importantly, the output layer is hardware realized with a bank of microring resonators. There is no latency due to feedback loops. Here, we just parallelize in wavelengths. And it was tested against some tasks, such as digital conversion. It was nicely done. And we have header recognition that you find in the thesis results are not that nice. There are many challenges and opportunities with this setup. Of course, you can optimize the learning algorithm. This was simply trial and error. One can try genetic algorithms or so. And one can try more complex nonlinearities. Here I was using a saturated amplifier, but maybe you want to use the interaction of 2 lasers. And of course, you can increase the computational speed because here I was using fibers, and you can clearly do a photonic integrated circuit for the delays. that's almost the end. We're going to wrap up everything that I did and look for next steps. So in summary, the main achievements are that increasing the bandwidth response of the time-delay reservoir is produced by an increase of the injection strength of the injection semiconductor laser. A faster response time of the system allows for a reduction of the virtual node separation. Then I have demonstrated that photonic signal processors, in particular stream learning machine, can compete against digital signal processing scheme, in particular this Kramer-Scrolling receiver that I was mentioned, for certain levels of noise and this experimental data recovery task. And lastly, I have shown you how to implement a tap-delayed neural network with this hardware output layer. And all the results are summarized in these publications. Here I just want to briefly mention of what can be done in the future. We know that in the input layer, in order to operate them faster, we have to overimpose an analog mask that matches this speed. For that, there has been work, but they are numerically, that are looking forward in that direction. If we think about the reservoir, of course, we want shorter delays in order to reduce the latency time. That can be easily done by photonic integration. If we think about the output layer, that is also doable in a photonic integrated circuit. In particular, there are these first demonstrators in which you see the different delay lines, and then this set of Mach and the interferometers to introduce the weights. And then just mentioning that you can go further and mix time and wavelength division multiplexing in order to create this kind of photonic accelerators that are implementing convolutional neural networks. And that's everything that I wanted to mention. And thank you, and I'm ready for the questions.
Okay, so thank you very much for this very nice presentation. So as I said in the beginning, everyone who doesn't want to stay to the questioning part is allowed to leave now.